This is my shiny hunting bot that's capable of finding the rarest Pokemon automatically while you do other really important things. And it managed to find a shiny Shaymin, Torchic and Poochyena all by itself, which we're super proud of it for. But to be honest, it has quite a few glaring issues that I glossed over last time, just to keep the illusion alive. But now it's time to break down what's wrong with this old bot here, and how version 3.0 of the Shiny Hunter is going to be a lot better. So the first problem with it is quite an obvious one. It is an absolute mess. The wiring is all over the place, the breadboard is far too big for the small components, and it's extremely flimsy, making it really hard to transfer anywhere, which is why it was sat on this Amazon packaging. The fact that the Arduino controlling it, the breadboard circuitry and the DS itself were three separate items held together by a few loose wires was a terrible design, and something a bit more cohesive is needed this time around. The programming is also another massive issue. The way that it's set up is extremely rigid. I had to manually write out the exact sequence for a specific hunt with all of the inputs and delays, meaning I couldn't just pop a new game in and hunt for a different Pokemon without completely new code. So for example, this bot hunted for a shiny Torchic in Sapphire, but if I wanted to hunt for a shiny Bulbasaur in Leaf Green instead, the process is completely different and it would not work at all. So I need to design a way to be able to easily adapt to different hunts and tell it which hunt it's currently doing, so it doesn't mistake it for something else. The final big issue with it is simply the fact that I was basically damaging a 20-year-old console by soldering dodgy wires onto parts that weren't supposed to be touched. So I need a new way to connect to the motherboard without ruining a classic device. I also need a more elegant solution to the screen checking, instead of just taping a photoresistor to the screen. So that's something to also consider. So let's get to planning a brand new ultimate shiny hunting machine. To start with, what new features do I want to include? Well, the first thing is probably the easiest to do, and that's the ability to actually move. I know exactly where the pins are on the boards to move, and I could have soldered them on in the last version, but I didn't. So that's a simple fix. Just add more inputs. And with moving, I can also add the ability to hunt for random encounters, and not just static ones, by spinning on the spot in a patch of grass instead of soft resetting. Again, it's very easy to do and will definitely be something I add. And again, in a similar vein, there are some hunts where the best method is to run away. This would have sped up my hunt for Shaymin a bit, as running away and re-entering the zone is actually faster than soft resetting. So those are the easy ones. What else do I want to do? Well, there's one thing that I spoke about avoiding in the last video, and that is visual detection and OCR. By using a camera pointed at the screen, I can get more accurate information than just timing the encounter can give me, so I think it's worth a try. By looking at the sprite's colour, I can visually determine whether or not a shiny has appeared, and can also just use the simple method of looking for a bright spot on the screen, just without the photoresistor taped to it. This is going to be one of the biggest challenges to get working, but that's all part of the fun really. If the camera is able to read the Pokemon's name, it can then look up the colour it's supposed to be in a specific area, and check against it, which would work well for random encounters where a whole bunch of Pokemon could appear. And finally, some way to store the data for each shiny hunt. When a shiny is found, the system can save the data to a file, saying that it took X amount of encounters to find this Pokemon, it started on this date and finished on that date, taking this many hours, something like that. So how am I going to actually achieve all of this? For starters, I'm going to be replacing the Arduino with something more complete, a Raspberry Pi. This is a Raspberry Pi 3, and the reason I chose this one specifically is because I had one in my drawer lying about, so anyway. With this, I can run more complex scripts, store a whole lot more on it, and overall make a better system. Raspberry Pis have general purpose pins on them for input and output, just like the Arduinos, and I'll be using these in a very similar way, just slightly more refined. When handling all of the inputs for the old version, I literally just wired every single one to a separate pin, which worked just fine, but caused a bit of a mess with the wiring, and it turns out there's a much better way to do it, and that is by using this simple component, a shift register. What this does is converts a serial input to parallel, and these ones I've got here, some 74HC595s, have 8 output pins. so 8 bits of data to handle for 8 different buttons. But if you've ever looked at a Game Boy Advance or a DS, you might have noticed that they have more than 8. But that's where the magic of these things comes in. They can be chained together for even more outputs. By connecting the serial out from the first one to the serial in on the second one, I can pass controls through the circuit and handle all of the buttons with 2 shift registers and only 3 pins being used on the Raspberry Pi to handle the data, clock and latch pins on the registers. This whole setup is a lot tidier than running 14 different wires to the Raspberry Pi and makes it a lot easier to code as all of the data goes through the same pin. For this project, I'm going to be diving into the world of custom PCBs and design my own to install into my consoles to replace the mess of cables. I checked out a few PCB printing companies to see if this was financially possible, and most of the sites were quoting hundreds for a handful of boards, and if I messed up the design in any way, I would be completely out of pocket. This issue was going to hold back this project because I just couldn't justify the price, but that was until I found JLC PCB. This is definitely not sponsored, but their pricing and easy service is the saviour of this project. I used a demo board design just to see a basic quote, and with shipping it was under $15 for 5 boards, which is a bargain compared to the rest. So this project can go ahead. Now to design the board. After some very basic planning, I have 2 methods that I think could work. These are spring pins, or piston pins, or probe pins, or whatever you want to call them. And what they do is create a connection to a contact with a spring-loaded force. You've probably seen these sorts of things on wireless earbuds or smartwatch chargers, and what I could do is use these with a PCB on top of the DS and press down onto the input pins, making the same connection as the wiring, but without having to solder directly to the board, preventing any potential damage to these classic consoles. I initially thought of simply using prototype PCBs to get this done. However, the standard hole spacing just doesn't line up with the DS or Game Boy Advance SP's board, so I would have to go fully custom. This is fairly simple to do, as long as I can space the pins out correctly. The second option, however, is a bit more advanced. If you've ever seen Nintendo DS or Game Boy mods, you've probably seen how they use custom, flexible PCBs to seamlessly integrate into the system. And that would be a really nice thing to be able to design, with a simple USB port on the side to transmit all of the data for the inputs. But the only problem here is, I think something like this is a little out of my reach right now, as I'd have to embed all of the shift registers and a chip to process it all on the board, and I really don't have the technical know-how to do that. So for a simplified version, I can have the flex cable hang out of the side of the consoles and handle all of the chip stuff on an external PCB. So which one am I actually going to do? Well, while I think that I could make the spring pin build work with a sort of sandwiched, deconstructed DS, I'm going to attempt to design a flexible PCB mod, because it seems like a real challenge. So let's design the circuit boards. As the DS and Game Boy are obviously 2 separate consoles, I'm going to need 2 separate board designs, but they'll really only vary in where the inputs are placed and the cables connecting them. To design custom PCBs, I'm going to be using KiCad, a design tool for PCBs, schematics, and basically everything electronics. I have these reference images for the DS and GBA boards, and by setting their scale correctly, I can simply draw the traces along and line up the pads perfectly. So I'm going to take a little time drawing these out, and I'll come back when I'm done. And here we are, I finished both boards. This is the Game Boy and this is the DS. For the first versions, I have the connections hanging out the side of the consoles here, and I've made sure to use the same pin layout for both consoles, with the DS having the 2 extras at the top, so that the code can be used seamlessly between both consoles. Each of these pads over the console is a simple solder point that I just have to solder down, and then on the other end I'll use little headers that plug into an external board that handles the signals from the Raspberry Pi. Brilliant. Now I just need to get these all ordered from JLC PCB, which is going to take a while, so it's lucky that I did this at the start of the project, and with a bit of movie magic, they'll appear. That was easy. So I have 3 boxes here from JLC PCB, and you may be wondering why that is. Well, let me peel back the curtain a bit. I first designed the Game Boy PCB for both the spring pin design and the flexible one, as I wasn't sure at the time what was going to be the best option. And this actually saved me a lot of time and money, because once I opened up this order, I realized that I kinda messed up the design. You can see the two here, and yeah, I didn't do the pads right at all. And these are just vias. A via is just a path through the board from one layer to another, and is not the same as a through-hole solder point. So these two designs are useless, but it's quite funny to be honest. After seeing this, I jumped back into KiCad and fixed the mistake for the other two, so let's take a look at those. Each order came with 5 boards, as that's the minimum you can get, which is good, because if I mess something up, I've still got spares. Here is the GBASP board. You can see all of the inputs, and if I bring in this Game Boy motherboard, I can line it up to every single pin, and amazingly, it's a perfect fit. Only thing that I would change for a better version is to reduce the size of the solder pads, because they're a bit too big, but that doesn't really matter in this case. And here is the DS one, which we'll get to later. I also need a control board that connects the consoles to the Raspberry Pi, and I'm just going to build that on a prototype board. This board is where the 2 shift registers are going to come in, with a header for the consoles and the Pi. Here's a little diagram of how this all works. The Raspberry Pi has 40 pins to handle power with both 5 and 3.3 volt, a few ground pins, and general purpose input-output pins, or GPIO for short. For this control board, all I need to pass through is power, ground, and 3 GPIO pins. And so I have picked out this top corner here with 2 pins for 5 volt, 1 for ground, and 3 GPIO. I need these to provide power to the shift registers to ground everything, and then pins for the shift registers data, clock, and latch. Using the 2 5 volt pins isn't necessary for this, I could have chosen one, but I have done this as it makes it easier to line up the header with the edge of the pins. The control circuit takes these inputs and connects them like this. The first 2 pins are for power, and they go to pins 10 and 16 on both shift registers. The ground goes to pins 13 and 8 on the shift registers, and also passes through to the header for the consoles. The 4th pin is the data pin, and that only goes to pin 14 on the first shift register. It doesn't connect directly to the second, and instead is connected from pin 9 on the first one to pin 14 on the second. This is how shift registers chain, by overflowing the data from one to another. Then comes the latch pin, which goes into pin 12 on both of the registers. This is, as the name implies, a way to open and close the shift register. So the latch opens, you feed the data in, and then close the latch so it updates. The final pin is the clock, which connects to pin 11 on both registers. This is used to iterate through the register. By sending a tick to it, it moves to the next bit in the line. That's the shift registers all wired up. It's then just a case of connecting the output pins to the headers for the consoles, with one going to each button. And here's what this circuit looks like. This is the first one I made, and while testing it, I did a really smart thing. By switching the 5 volt and ground around, I completely burnt out the shift registers and bricked it. So here's the second one I made. I'll try not to fry this one. And with all that, the circuitry is complete, and I now have to program all of the functions in Python, which I barely know, but I'm sure I can manage. So let's hop over to the Raspberry Pi. So like I said earlier, I'm using a Raspberry Pi 3 for this project, simply because I had one lying about from some old university module. And because that was about 10 years ago at this point, that makes this thing also 10 years old. And while it's still perfectly capable of doing what I wanted to do, getting there is a whole other story. I rarely ever use Raspberry Pis, Linux-based systems, or anything like that. And in fact, I think the only thing I've used this for since uni was to make a retro games console, so I'm not exactly experienced with it all. I tried to install Raspberry Pi OS, the standard operating system for these devices that has a desktop and programs just like a regular computer, except this thing struggled with that. Every single action was far too slow, and it was too painful to use. I was planning on using Raspberry Pi Connect to remote access into it, so that I didn't have to hook up a monitor or peripherals to it, but that also didn't work. Eventually, I settled on installing the light version of the OS, which runs the same stuff, but doesn't have a desktop environment at all, and operates exclusively through the command line interface, which might as well be alien technology to me. So I'm using a system I don't know much about, with an interface I've never used, and coding in a language I don't know. What could possibly go wrong? To program this project, I am just SSHing into the Raspberry Pi and coding in Nano directly. This means there's no autocorrect, there's no syntax checking, basically no help at all, but here's what I've got. The first function I wrote up was a basic one to iterate through all of the outputs on the shift register. It takes in a number, And if the output index matches that number, it's set to low, which pulls the pin to ground, which in turn triggers a button press. All of the other buttons are set to high, and then I just add a short delay before resetting them all to high, so the button doesn't stay held down. But this only allows one button at a time, so I need to change it so that it's an array of numbers for when multiple buttons need to be held at once, like a soft reset. I also want to add another variable for a delay, which will just be how long to hold the button down for, so if I want to walk in one direction, it's not just tapping the button repeatedly. So I'll just write that up and I'll show you a little live demo. And here we are. I've got the Game Boy attached at the moment, and if I call my Python script here with 10 as the button index and 2 for the hold time, in game you can see I am now walking right for 2 seconds. Brilliant. The next thing to add is some definitions for the buttons, as it's a little hard to remember which number corresponds to which, and I'm also going to add a new feature that I think would be rather cool. So I'll be right back after this epic programming montage. What does that mean? Please work, come on. Why are you like this? There we go, that was, super easy. Well, anyway, here's how it works now. Instead of being a one-shot program, it now loops and waits for input every cycle. To make sure it doesn't get stuck, I added a quick command, just in case. So now, I can type in a command, so up 0, and it'll tap up. Or down 2, walk down for 2 seconds. But I don't have to type any command at all. And instead, I can do this. I am now playing Pokemon Fire Red with an Xbox controller on original hardware. Is this cursed? I'm not sure, but it's pretty great. So let's just go over the Python code I've got running here. These are 2 separate scripts just for my sanity, for the commands and for the controller. For the commands, I set up this dictionary called button index that has all of the button presses as the key and their corresponding index for the shift registers as the value. When I input these commands, it checks if the command can be found as a key in the dictionary, and if it can, it presses it down. And it's basically the same for the Xbox controller, except it translates the controller buttons into commands first, and then into the index values. It is so much more comfortable playing with a controller, and if I pair it with a TV out mod, I've got my very own consolizer. The next big step for this project is to get the sequences in, and because I want this to work with different games, I need a way to define what sequence goes with what. And for this, I'm going to use a simple CSV file that has the headers for the game, method, and sequence. So the game and method fields are pretty self-explanatory. For example, FRLG for Fire Red Leaf Green, and RE for random encounters. But the sequences are a lot more involved. Let's look at how exactly a random encounter works in Fire Red. The first thing is to identify the point where the loop begins. And for random encounters, that's actually in the battle menu. As the shiny check is at the end, and this method doesn't require resetting in any way, the first step is technically to run away from the current target. So from this battle intro screen, where it says a wild Pokemon appeared, it needs to press A, wait 2 seconds, go down, right, and A again to run. It then needs to wait a few seconds before looping left and right steps until a battle starts, where it would then wait a few seconds and finally check the screen before looping all over again if it's normal. But how do I give it all these different commands? That's actually really easy. If I write out these commands in the CSV like a normal list with button inputs being text, delays being numbers, and using keywords for specific actions, I can translate this into a list of commands. When the list is read, it passes the data. If the string is a valid button, press that button, just like the previous commands. And if the string can be converted to a float, it must be a delay. If it says loop, then it checks through the list until it finds the keyword end, which signifies which commands to loop. So in the random encounters, it has loop left right battle end. So it moves left and right repeatedly until it detects that it's entered a battle. That will come later with the camera stuff, so for now it will just loop infinitely. And finally, the check keyword, which will trigger the camera to look at the screen and determine whether or not the Pokemon is shiny. To write out the sequences, I just wrote a simple Python script, but if I ever revisit this project, I'd make a nice interface to handle that instead. And now for the big one, the camera system. What I plan to do is use the camera to check the screen for when a battle is entered by simply scanning for a black screen, and for checking if a Pokemon is shiny by comparing color values at specific points. Ideally, it would read the Pokemon's name as well to know which colors it's looking for, instead of just looking for differences. I'm going to take some time to have a go at all of this, find out what's the best camera library to use for it, and how I actually do any of it. And hopefully, you'll be able to see something in action. Okay, I've been at this project for a while now, trying to crack this camera stuff, and it's not looking good. I'm using the basic V1 Raspberry Pi camera module for this, and it's just not good enough for what I'm trying to do. I've played around with some basic OCR by just spitting out anything it can see, and the results are so messy and inconsistent because the camera is struggling to take clear pictures. And when I try to point it at the Game Boy and DS screens, it's even worse. So let's play a little game. One of these images is a screenshot from an emulated version of the game, and the other is a picture captured by the Raspberry Pi cam. Try to guess which one's which. If you said option A was the Pi camera, please go and see an optician. If I zoom in on the actual Pi camera one, it's clear to see why it couldn't make out any words here. That is a noisy mess. I wrote a little test to simply measure the brightness of the screen to know when I've entered a battle, similar to how I did it before with the photoresistor, which does technically work. You can see the value dips when the screen goes off, but it's so susceptible to background lighting, so unless I build a box to put all this in to block out every other light, it's not going to stand a chance at detecting a shiny accurately. So what am I going to do? Well, it's clear the camera has to go, and I need something better, because without a good camera, I have no chance. So I'm going to sink even more money into this project and order a newer, better camera module that hopefully fixes my problem. So let's see, shall we? Here it is. This is a Raspberry Pi camera version 2.1. Not the latest version, but still supposedly better than the V1 I was using. So if I load it into my lovely camera mounting system, line it up with the screen, and run my test code, we'll find out if this upgrade was worth it. Wow, it's beautiful. I can actually tell what is going on in this picture. The text is clear, the colors are pretty accurate. Maybe I can work with this. So I want to get this to use OCR, or optical character recognition, to identify which Pokemon it's looking at, so it knows what colors to check for. It sounds simple enough, but I doubt it will be. So let's see what happens when I run the image through Tesseract. Ah, yeah, those aren't words. It sometimes vaguely gets it right, but then goes straight back to gibberish, and that's because these models are trained and are looking for clear text that is a nice plain font. This is none of those things. I'm going to take a while and see what I can do.
One eternity later.
This one problem has eaten away hours of my life trying to get right. I tried every trick in the book to get it to be readable. Grayscale the image, upscale it, apply a Gaussian blur, denoise the image, apply binary and adaptive thresholding, all of the above at once. None of it was enough to get these lightweight models working on the Raspberry Pi. If I take a picture and feed it into a larger, more capable model on my PC, it has absolutely no issue whatsoever, but that can't run on a Pi, so no luck there. I was smashing my head against my desk, trying to think of ways to get this thing over the line, because failing out was not an option. And so here's what I came up with. OCR, object detection, any fancy thing like that, but straight out the window. And instead, I resorted to a very basic technique that works nearly flawlessly. By running the images through the processing I just mentioned, I just simply count the white pixels to see if they're above or below a certain level. This is a very similar method to the photoresistor last time, but allows me to pick out more detailed parts. When the battle starts, for example, I scan the bottom right part of the screen. And if there's a large white blob, that means the menu's popped up. If the screen goes dark when I'm running back and forth, well, that means a wild encounter started. And the most subtle one, if the wild Pokemon appeared text appears within 5 seconds of the battle starting, that means it's not a shiny. With these 3 checks, I can repeatedly random encounter Pokemon until a shiny appears. And let me tell you, the amount of relief I got when this thing worked is insane. It's so rewarding watching it run on a loop, hunting for a shiny after spending so much time getting it working. And I left this thing going for a while. And I managed to find a shiny Zigzagoon in the same copy of Pokemon Sapphire that I used to get Torchic last time. And just for fun, I set this guy off with my copy of Pokemon Pearl. There's a cute charm ID, which basically makes shinies insanely common. And in the span of 10 minutes, it found 4 shinies, which is just laughable. And that is my new and improved shiny hunting machine. This thing is capable of hunting for starters, static encounters, random encounters, and maybe even eggs if I can get the programming just right. But it does still have some issues. On the hardware side, it would be great to enclose everything inside the DS, placing the shift registers on the flex PCB or replacing them with a little microcontroller. I opted to go with the external board just as this was my first time designing PCBs, and I knew that if I got it wrong, it would cost me a lot of time and money. Case in point, the time I burnt out the first shift registers. And I think I could take it one step further. By implementing some sort of processing chip and adding a USB-C port to the board, I could replace the old charging port and have the data and power carried through the same cable, making it a whole lot tidier and easier to use. One of the biggest issues with it still is it's very susceptible to the light around it. Going from daylight to bright room lights really throws it off, and if I dare to move and cast a shadow, it will throw everything off. This issue is basically down to the fact that the DS and Game Boy screens just aren't that bright and have pretty bad glare issues. So if I did something similar to this on a Switch, for example, it wouldn't struggle at all. But I do have a great solution to this. That means I wouldn't rely on a camera at all. By using a DS capture card, it can read the screen directly instead of using a camera for perfect image clarity at any time of day. And I do actually have one of these. It's just in a DS that's in a drawer somewhere in another country, so I never got to try it this time around. If I do tackle this project again, I would also ditch the old Raspberry Pi and make a desktop app that shows all the details in real time, including a screen preview. Because saving files and then copying them to my PC through PowerShell every single time I need to check a frame has been a bit of a nightmare. But there we go, a shiny hunting bot. I just wanted to say thank you so much for the support on this project. It was so amazing seeing the responses I got on the last video, and I hope you like this one too. I've put a lot of time into this, and it's nice to know that it wasn't all a total waste. But anyway, thank you for watching. Leave your feedback down below, and I'll see you in the next one. Cheers.